directions. In all directions. And continuous locus of all particles vibrating same phase. Just a moment. At any instant. It's called a wavefront. It's called wavefront, right? So there are three types of wavefront we should know. First one is, let's say, the spherical wavefront.
Locus me.
Right? So spherical wavefront means what? Suppose if there is a point source, right? So point source is going to send the light in all the possible directions. Right? So this is the point source. You can consider it like a bulb, right? So it's going to send light in all the possible directions like this. So consider after some particular amount of time, right, the ray which started from here are going to reach at same particular distance, right? So all those points you can consider, this point, this point, this point, right? All these points are in same phase, we can say, right? So as long as the distance is same, right? So I can draw the, let's say, circle like this. In 2D, it will look like a circle. If you consider this in a 3-dimensional, you will be able to find it as a sphere, right? So therefore, we can say all those points on that sphere will have the light at the same time. They will get the light at the same time, right? So that we can call it as a spherical wavefront. Consider these points also. These points also will get the light at the same time from that source, point source, right? So this is also another wavefront, we can say. This is a spherical wavefront. What else we need to know? So another one is, let's say, cylindrical wavefront. Consider there is a small tube like this, right? So tube of light, we can say, right? So it is also going to send the, let's say, light in all the possible directions. So if you consider the distance at which the light will reach simultaneously, right, will be something like this. In 2D, it looks like this, right? What you can say in 3D, it will become something like this, right? So that looks like a cylindrical wavefront, we can say. That will be the cylindrical wavefront, right? Example, obviously, the tube. Third wavefront you can consider is a planar wavefront. So plane wavefront means what? Let's say, suppose line is all the light beams are in parallel direction. Okay. So in that case, what will happen? These points, this point, this point, this point, this point, all will have the light at the same particular time. Right? So in 3D, it will look like this. So this is a plane wavefront, we can say, right? Why we do need this plane wavefront, cylindrical wavefront? Because there is one derivation, important derivation, that is the law of reflection as well as refraction using this wavefront. Right? Now, the example of this plane wavefront, you can consider it as the light source which is at an infinite distance. Infinite means longer distance, we can say, right? So for example, sun, right? sun is at infinite distance. So even though sun, we can treat it as a point source, right? It is sending the light from or towards all the directions, right? But is it going to give us the spherical wavefront? No. Remember this concept very importantly. Sun's wavefront is not spherical wavefront, even though it is sending the light to all the possible directions. Because sun as a light source, we consider it as a at infinite distance, long distance, right? And the light beams coming from the long distance are considered to be parallel. Therefore, they are going to give us the plane wavefront, right? Then next part we need to remember is Huygens principle. So Huygens principle says that every point on or on, let's say, primary wavefront, we can say primary wavefront. What is primary wavefront? So let's say this wavefront, we can say simple. So this one, that red color thingy, let's consider it as a primary wavefront. Okay, so every point on that primary wavefront, so all those points, they are all going to get the light from that point source at the same particular time, right? So every point on the primary wavefront acts as a source, right? Sending out disturbance in all the directions. Just like the original point source, you can say, right? Like that. And so because of that, what we are going to get? We are going to get the another wavefront. Right? So the new position, we can say, the new position of wavefront at any instant is called as secondary wavefront. Secondary wavefront means, let's try to understand this concept. So what we know, suppose if you consider this parallel line, initially the line is parallel, right? So consider this is the line, and every point on the let's say this parallel primary wavefront. So consider this is our primary wavefront. I will show you. Right, in 3D it looks like this, in 2D it will look like this, right? Now every point on this primary wavefront is going to act as a secondary source, right? It's like a light source, we can say, right? And it is going to send another wavefront. So that is like a point source. Now point source will send you this, give you the spherical wavefront, right? So the wavefront will look like this. So this is the wavefront of all these point sources now, which are actually nothing but the single points on the primary wavefront, like this. And if you draw the tangent to all these wavefront of the point sources, you are going to get it as a secondary wavefront. So this wavefront, you can call it as secondary wavefront. So this is the principle you need to remember about the Huygens, right? That every point will act as a secondary source, giving out the secondary wavefront, right? Next. Then now there is one important derivation we are going to do, that is the law of reflection by Huygens principle. Huygens principle. Right? Let's try to understand what it says. So already, if you remember, The law of reflection, we know that if there is a mirror like this, which has the incident ray normal like this here, making an angle I, right? And this is the angle R, and we do say angle I is equal to angle R. The same thing we are going to use using the Huygens principle or Huygens wavefront concept, right? So let's see how it works. So this is a derivation they might ask in the exam. Very important derivations, right? So what I can say, suppose if there is one light beam like this and another parallel light beam I can show, right, which is going like this. Now, if I draw the perpendicular to this perpendicular, I can call it as a wave front, right? That is our wave front. We already have seen if the light beams are parallel here, right? We'll get the perpendicular. This plane, you can say that this plane is perpendicular everywhere, right? Wave front is always perpendicular. Here also you can see this is also perpendicular everywhere. Here also, right? So when these two, let's say light beams are going like this, instead of saying the light beams are going, we will say the wavefront is moving in the forward direction. Wavefront, let me name that as AB. Wavefront A and B. Okay? Again, we have this normal. Now, what is going to happen at this particular point? The first beam already reached the mirror there. So if it already reached the mirror, then what will happen? It will get reflected. So it will get reflected like this. Let me show the reflected ray by this green color, right? Okay. But the second wavefront, you can see it is still in the first mode. It is in the, let's say, first phase, right? It is not reflected. So it is still going into the straight line like this, right? So first beam already got bent because of that reflection, and second ray will reach, let's say, here. Okay. And after that it will reflect, and again when it will reflect, obviously it will go parallel. Okay. So like this. Again, if I draw the let's say this, let me draw it like this. If I draw the perpendicular here, this perpendicular, let me call this as A dash and B dash. Okay. This will be the reflected wavefront, I can say. Correct. Now our job is to prove what? Our job is to prove this angle I is equal to angle R. Right? So if I can say B dash is a distance covered by the light in, let's say, some particular time t, right? So what I can say, B dash is equal to C into, let's say, delta t. Why C into delta t? Because we know that distance is equal to speed into time, right? Similarly, so at the time when the B reaches at B dash, right, the light beam from the A will reach to A dash. So I can also say that A dash is also C into delta t. Delta t is the time. This is the time. The reason is same, right? So in the same time, as the light is moving in only one medium, right? In reflection, we only have the one medium, right? So as long as the medium is same, the distances traveled by both of them will be same, right? So what you can say in these two cases, I can see the two triangles there. So triangle, let's say A, B, B dash, and triangle A dash, B. So A, B, B dash, and A dash or A dash, B, right? So in that, what I can say, first of all, this AB dash, this length is common, right? So let's say AB dash is equal to AB dash. It is common side in both the triangles. So obviously it is equal. Right? Then we also said that AA dash and BB dash both are same because both are the distances traveled by the light. So let's say AA dash is equal to BB dash. Plus that angle you can check there. So that angle, let's say angle ABB dash is congruent to angle A dash B. Why? Because both are 90 degree. Reason is both are 90 degree. So therefore, what I can say, triangle ABB dash is congruent to triangle AA dash B dash, right? Using the right angle rule or right angle hypotenuse rule, right? So RH rule you can say. So if these two are same, so now let's also try to understand which angle is I, because our ultimate job is to prove this one. Angle I is equal to angle R, right? So what I can say, if this is the angle I here, right, then this angle will be 90 minus I, and this angle will again be equal to I, right? Similarly, your R angle, you can say this will be the R angle here. Okay. Again, you can work out using the geometry a little bit, that like we did here, angle I 90 minus I, right? Similarly, initially you will say this is angle R, then this one is 90 minus R, so this one will be become R, right? So like that. So I'll remove this. So once we got the similar triangles, what I can say, that angle, let's say this one, angle BAB dash, angle BAB dash is congruent to angle, let's say A dash B dash A, and that is nothing but your angle I is equal to angle R. Hence, so this is the one small derivation, but important, right? Law of reflection as well as law of refraction. They might ask you to prove. So this is the one of them, that is the law of reflection. Okay. So any doubt in this? Go through this. Let me know if there's any doubt here. Okay. Chalo. Now the next important derivation you have is the law of refraction, again by the Huygens principle. Okay. So let's see how we can do that. So law of refraction by Huygens principle. So in refraction, we know that, so suppose in the ray optics you have studied this. So this is like, say, the water or the denser medium. So when the light goes like this, the normal angle I, right, light bend towards the normal, right? Right. So this one is angle R. Okay. So this is your rarer medium, and this one is your denser medium. And in this case, what we need to prove, that sine I upon sine R is equal to refractive index. Right? So refractive index, you can call it as n or mu. Right? Then, so using the Huygens principle, what we are going to do, how to solve this? So again, let's say this is the denser medium, right? So this one is denser, this one is rarer. So we have the two rays, right? Two light beams, right? In the Huygens, we are always going to use the two light beams like this and a wavefront connecting them. So these are the two waves. Right? Again, if same thing, if I draw the perpendicular here, this is your A, this one is your B, right? So let's say this is your normal here. Another normal I can show here. What we know that this angle is I. Okay. Now, again, the first beam and the second beam, same thing. First beam reaches the interface of that medium, right? That medium, we can say, at the same time, right? And if it is reaching at the same time, first time, right? A beam will reach at the first. Okay, B will reach after some time. So what I can say that this ray is now going inside the water, and we know that it bends towards normal, right? So this is your angle R. Now what we are going to say, suppose the first one is a air. So speed of light in air is, let's say, c, and speed of light in a, let's say, denser medium, right, is, let's say, v. So consider that when the A ray starts from here, right, it reaches, let's say, at A dash point, right, and the B is still in the first medium, right? This is our first medium, rarer medium, let's say. This one is your second medium, denser medium. So the let's say first beam is going into the second medium, denser medium. Second beam is still in the first medium, right? So in that case, what we can say that velocity of light of the second medium is c. Sorry, not second beam, I can say, in the first medium is c, right? And the velocity of the first beam, which is now in denser medium, its velocity will be v, right? So obviously we know that speed of light in air is more, that is highest, right? And that velocity in the medium is the lowest one, right? So what I can say, distance covered, let's say if the first beam reaches, let me call this point as A dash, right? Because B is going to travel more distance. The second ray is going to travel more distance because it has the higher velocity. Let me show the A dash somewhere here then. This is A dash. This one is B dash. If you join this, wavefront will look like this now. Okay. Again, first of all, try to work out the geometry. This one is angle I. This one is angle 90 minus I. This is also angle I. Similarly, this one is R. This will be 90 minus R. Again, this is R. Right. Now, if you talk about the BB dash means what? Distance traveled by the light in the first medium, let's say in the air, with the speed c in a time, let's say, delta t. So what I can say, BB dash is equal to c into delta t, right? Where delta t is time, so distance is equal to speed into time, right? Then a dash. Now a dash is also the say distance traveled by the light, but with the different speed. Different speed means that v into, let's say, delta t. Delta t is again time. Okay. So first of all, what you will do, you will divide these two equations. Let's say this is equation number 1. This is equation number 2. Divide 1 by 2. What you will get? BB dash upon A dash is equal to C upon V. And C upon V is nothing but the ratio of the velocities, and that is also equal to the refractive index of the medium, of second medium with respect to first, right? So what I can say, this is nothing but your refractive index. BB dash upon A dash is equal to n of second medium with respect to first, right? Why? Because we know that C upon V is equal to refractive index, right? Refractive index n. Now again, if you take a look at AB dash triangle, so let's say triangle AB dash, I can say sine I is equal to opposite. Opposite is BB dash divided by hypotenuse is AB dash. Okay. Another triangle, consider the another one, sine A dash B dash, right? In that I can say sine R is equal to opposite. Opposite is your A dash upon again AB dash. So let's call this as equation number 3. This as equation number 4. Divide the equation number 3 by equation number 4. What you will get? Sin I upon sin R is equal to BB dash upon AB dash divided by AA dash upon AB dash, or sin I upon sin R is nothing but BB dash upon A dash. So from this equation, we can see that it is nothing but your refractive index. So sin I upon sin R is, therefore sin I upon sin R is equal to refractive index. Let's say N21, right? So this is how we can prove the Snell's law. This is also called as a Snell's law, right? If you remember from the ray optics. Hence, so these two derivations are very important. Let's say in the written examination, they do ask this many times. They have appeared many times in the previous year questions also, right? Okay. Now, now the next part which we are going to do is a interference of light. Okay. Interference of light. So in the interference of light, what we can say that phenomenon of redistribution of light energy, redistribution of light energy in the medium due to superposition of two light waves. Two light waves. It's called interference, right? So first of all, statement is important. It's called interference of light. Some more terms you need to know in this one, which they can ask as a statement. So first one is, let's say, sustained interference, that you can remember. What is interference? Interference means a superposition of light waves, right? Two or more. Generally, we do consider two light waves in the Young's modulus, right? Sorry, in Young's double slit experiment, right? So, but it could be two or more sources also we can consider, right? So another thing is sustained interference. So here you can see the pattern of equally bright and dark fringes of same width developed on screen. That we can call it as a sustained interference, right? Equally bright and dark fringe of the same width, right? Because in interference in IDSE also we use the same width bands, whether it is a dark band or the bright band, right? Then another one is the coherent sources. So now what is coherent sources? So these are the sources which emits the light of which emits the light of same frequency and it's in same phase. It's in same phase or have same phase difference. That we can call it as a coherent sources, right? So they can ask you that what are the conditions for sustained interference, right? So sustained interference means we already have seen there must be equal bright and equal dark fringe or same width bands must be there. So what are the conditions? So that is another question they can ask. Conditions for sustained interference. First one, they must be coherent sources. It's two sources we need to have. Those must be the coherent sources. Another, the sources must be, sources should be close to each other. Close to each other. Third, sources must be narrow. Narrow means pinhole, you can consider that is pinhole. Means point size sources must be there. That we need to understand. Then let's talk a little bit about the constructive interference and destructive interference. Right? We already have said that there must be bright band and the dark band. When we say bright band means what? The light due to, let's say, two sources, two coherent sources, when they are in a phase, right? We can call them as a bright band. They will form the bright band, right? And when the lights are in opposite phase or out of phase, then what we can say? In that case, that will be the dark band we can say, right? So let's try to understand the constructive interference or constructive, let's say the maxima also you can call it as. So constructive interference. So consider there are two waves like this. First one is like this. And second one is like this. Now what we can see in this case, these both waves are in same phase. I guess I need to redraw this. So both of these waves are in the same phase, right? They are moving together. So combination of these two, right? What we can say, that will create the maximum amplitude like this. That is also, we can call it as a superposition of waves, right? And now let's talk about the destructive interference. In that case, what I can say, this is so first wave will be like this. So consider this is the first wave. Second wave, I can show it like this. If you these combine together, what will get? The effect will be zero, null effect will be there. This will be the effect. Okay? So that we can say the destructive interference. Okay? So constructive interference, we can also call it as a maxima. Similarly, destructive interference, we can call it as a minima. Constructive interference will give us the bright band. The destructive interference will give us the dark band. So simple, if the two waves are in same phase, you'll get a constructive interference or bright band. If they are out of phase, then we will get the destructive interference. That means minimum. So now intensity, if you talk about the intensity of the two waves, right? So we should know that intensity is directly proportional to amplitude square, right? If we have the two sources, intensity by the first source will be I1 is equal to K A1 square. Then I2, I can say I2 is equal to K A2 square. So if I combine these two, then I will get the Imax. Right? So Imax, we can say it is a K and let's say A1 square plus A2 square, right? And similarly, I mean, I can say, actually, we also have to consider the, let's say, phase angle between them. So we'll say this is A1 plus A2 whole square, right? If they are in phase. Right? For this, actually, we use the formula R is equal to under root, right? Let's say A1 square plus A2 square plus twice A1, A2 cos phi. If they are in phase, means cos phi, cos 0 is 1. So this whole thing will become, let's say, A1 plus A2 whole square. Okay. So this is how we can write, like the Imax is equal to K into, let's say, A1 plus A2 whole square. Similarly, if you talk about the I mean is equal to K A1 minus A2 whole square. Okay. Now, in a special case, if there is a coherent sources, in coherent sources, we can say that amplitude is, let's say, we are going to consider it as a 1. Like in Young's double slit experiment also, we use the sources derived from the same primary source. So in that case, if A1 is equal to A2 is equal to A, then what we can say? Imax will be A plus A square is twice A square. Let's say 4 times A square. Or K is also there. Okay. Or we can also call this as 4 times original intensity, right? So if the original intensity of both of them is, let's say, I, right? So if A1 is equal to A2 is equal to A, then I can also say I1 is equal to I2 is equal to I. Okay. So I can also call this as 4 times I. Okay. Similarly, here also I can say if A1 is equal to A2 is equal to, let's say, A, then I mean will be this A1 minus A2 will become 0. Right? So I mean will become 0. Okay? So maximum intensity is 4 times the original intensity. That's why we got the bright, we'll get the bright point at that case. Right? And when you talk about the minimum, I minimum is 0. 0 means no light. No light means dark band, we can say that, right? Like this. Then one more small formula we can remember, which is handy to solve some simple numericals. That is a relation between, it's a phase angle phi and delta x. Right? Delta x is a path difference, right? So path difference means what? Let's say if the two lights are reaching at the same particular point from the two different sources, right? So these are the two sources. This is like a screen which we are going to use in Young's double slit experiment also. Right? So from this, if it reaches here, the second light reaches from the second source. So let's say yes 1t, this is yes 2t. So path difference, right, between that two, we can call it as a delta x. And how to decide whether these two lights are in phase or out of phase? So for that, what we can say that phi we are going to use, right? Next. So delta x is equal to the simple relation we will remember between these two, that delta x is equal to, or remember it like this, phi upon 2 pi is equal to delta x upon lambda. Okay, so this relation, or if I take the 2 pi to the other side, that will be 2 pi upon lambda into delta x. Now let's try to understand the for constructive interference and destructive interference, what will be the values of delta x, that is path difference, right, for two waves. Now we know that these are the waves. So consider if the one of the light is a sine omega t, let's say a sine omega t, right? Then y2 I can say is b sine omega t plus phi. Y1 is a sine omega t and y2 is b sine omega t plus phi. So when they meet together at some particular point, so the first wave is y1, second wave is y2. When they meet here, there will be a superposition, we can say, right? So superposition of two waves means what? Addition of these two. So y is equal to y1 plus y2. A sine omega t plus b sine omega t plus phi. Now we just have to derive this a little bit. So I can say this is let's say a sine omega t plus. Now here we are going to use the sine a plus b formula, right? So what is the sine a plus b formula? That is sine a cos b plus cos a sine b. Okay. Let's try to use that formula here. B, this is sine omega t cos phi plus sine phi cos omega t. Okay. Again, what I can do, I can just segregate. I will just give this b here. Okay. This is b. I can give the both to both of them. Right. After that, let's say the terms which contains the sign, right? Bring them closer, right? So let's say sine omega t here and here. I can take the sine omega t outside of both. This will become sine omega t in the bracket a plus b cos phi. So remember, this is like a third derivation of this chapter, third important derivation, I can say, right? Because they will ask you to find out the conditions for the constructive interference and destructive interference, right? So this derivation we can use. Next one will be, let's say, the Young's YDSE differentiation and the diffraction. These 4 to 5 derivations, if you do, so that will help us in the exam, right? So another one you can say is, let's say here, b sine phi and cos omega t. Right? Now what I'm going to do, this one bracket I can say, and this another bracket, let's say. Okay, this first of all, this bracket, I'm going to call this bracket as r cos theta. This is r cos theta. And this part I'm going to call it as a r sin theta. Right? So let me call that as r sin theta. Right? And that cos omega t as it is. So what is the use of that? This I will separately write here, that r cos theta, I have called that r cos theta as a plus b cos phi, right? What is a and b? A and b are the amplitudes of the light. So a and b are the amplitudes, you can say. Then the another one you have is, let's say, r sine theta. So r sine theta, I have called it as for, let's say, b sine phi, right? So I'll separately write it here. Now from these two, first of all, take the r outside. Okay. Then what we can say, this is sine A cos B and sine B cos A, right? So again, we can use the formula of sine A plus B. So that will be omega t sine omega t plus theta, I can say, right? Now ultimately, this will become R sine omega t plus theta. Okay. This is the, let's say, combined equation of the light by the two sources. Now let's come to this point. So r sine theta and r cos theta. Now in this case, r is our final amplitude, right? According to this relation, you can say r represents the amplitude according to the standard wave format, we can say, right? So how to find out the r? For that, we are going to square both the sides here. Square both sides and add. So what will happen? This will become r square cos square theta plus r square sine square theta is equal to, now square of this, that will be a square plus 2ab cos phi plus b square cos square phi. What I did, I just expanded this bracket, right? We know the formula, basic formula, x plus y whole square is x squared plus 2xy plus y square. Same formula. Plus r square sine square theta means square of this. That is b square sine square phi. Now, from these two, I will take the r square common. Cos square theta plus sine square theta. Here, a square, we can keep it as it is. This 2ab cos phi, let's keep it as it is. Okay. Plus, now these two. From these two, I'm going to take the b square outside. So in the bracket, I will have cos square phi plus sine square phi. Okay. So this whole thing we can call it as 1. So this is r square is equal to a square plus 2ab cos phi plus b square. Okay. So ultimately r will be what? R will be under root a square plus 2ab cos phi plus b square. Okay. So that is the expression for the final amplitude. Right? Now, using this final amplitude, we can find out, let's say, the maximum intensity or minimum intensity, right? So now R is the amplitude, right? And A and B are the amplitude of the two waves, right? Similarly, so if I say the first wave, amplitude is A, and the intensity, let's say I1. For the second wave, amplitude is B, intensity is I2. Okay? And combination of that means the resultant is R, and let's say the intensity is I. Okay? So what we got? R is equal to under root A square plus B square plus twice AB cos phi, right? Or I1 is directly proportional to A square, I2 is directly proportional to B square, and R is directly proportional to I square. Sorry, I is directly proportional to R square. So first of all, what I will do, I will square this. So this is R square is equal to A square plus B square plus 2AB cos phi. Okay. So if R square means what? R square is I. A square is I1 plus B square is I2 plus twice root I1 root I2 cos of phi. Right? So this is the intensity. Now, for the bright band or the constructive interference, what we say that the intensity must be maximum, right? So let's see. So once we got this formula, this is the derivation for constructive and the destructive conditions. When we will obtain the destructive interference, when we will obtain the constructive interference for that, right? So let's say for constructive interference, right? For constructive interference or the bright band or the maxima, right? Or bright band or maxima. What I can say in this case that I will be I max. I means this I. The value of I will be maximum if this cos phi will have the value 1. Why? Because cos phi takes the maximum value as 1. Cos phi is always greater than minus 1, but sorry. So cos phi is less than 1 and greater than minus 1, I can say, right? So maximum value of cos phi is 1. Okay. So I will be I max if cos phi is maximum or 1 is equal to 1, I can say. So at which angles cos phi can take the maximum values? So it can take the maximum values at 0, 2 pi, 4 pi, 6 pi, so on. Or I can also say it will take the maximum value at plus minus 2 en pi, right? Where value of en could be 0, 1, 2, so on. Now, if we know this, then what we can say delta x is equal to n lambda, right? Why n lambda? Because phi, we already know the relation between these two. Let's check the relation. So phi is equal to 2 pi by lambda into delta x. So if phi we got as 2n pi, then what I can say 2 pi upon lambda into delta x is equal to 2n pi, right? So phi means what? It is a phase difference. Phase difference. So what is the condition for the constructive interference? The phase difference must be even a multiple of pi. Or if you talk in terms of, let's say, a path difference, delta x is what? It is a path difference. So what you can say here, that delta x can take the value. Which values it can take? So 2 cancel, pi cancel, right? So delta x can take the values n lambda. Again, n could be 0, 1, 2, so on. So these are the conditions. So phase difference must be even a multiple of pi, or phase or path difference should be integral multiple of lambda. That is the condition for what? For constructive interference, right? Now let's talk about the destructive interference. Or destructive interference, that is a dark band or minima. In this case, what I can say, intensity must be minimum. So intensity will be minimum if cos phi's value is minimum. Okay. So what is the minimum value cos can take? It is equal to minus 1. Okay. So I can say it is a minus 1. So what we can say from this, that phi cos is minus 1 at which values? That is pi, 3 pi, 5 pi, so on. Or we can say phi is equal to odd multiple of pi. So like this. Here we said even multiple of pi. Here we are going to say odd multiple of odd number is represented like this, where n can take the values 1, 2, 3, so on. Okay? So this is the again the phase difference. If you want to talk about the phase difference, then we will say that pi or the phase difference is odd multiple of pi. If you want to talk about, let's say, the path difference, what you will say, 2 pi delta x upon lambda is equal to 2n, just a minute. We can say it is a 2n minus 1 pi. Again, if you do the calculation here, what you will happen that that pi will get cancelled, right? Then that 2n minus 1 will remain as it is, right? So this is 2n, this I can say 2n minus 1 pi cancel. So delta x will become 2n minus 1 lambda by 2, or odd multiple of lambda by 2. Again, n can take the values 1, 2, 3, so on, right? So like this. So this is the condition for the constructive as well as destructive interference, right? So these are some important derivations we have done today for the examination. Plus additional derivations which you can try is like a YDSE, obviously the very important derivation, diffraction, fringe width derivation. Okay, so those two extra derivations you can try, and all those 4 to 5 derivations we have done today, those are also very important. Okay, so today we are going to stop here for today. Thank you very much. Have a nice day.